Okay. Okay, hopefully this lowers the latency. I turned that down now that I have a new, better internet connection. Um, and welcome to, I'm going to turn the mic up just a little. And welcome to, hang on, I'm going to get the mic a little closer if that helps. All right. A little more central. There we go. That helped. Okay. And great. And welcome to our last lecture in the Prolog Essentials series. Looking at the constraint as the, I can live with that. Let's see. CHR is mind twisting. It's thinking in terms of state. Yes, it is. Yes. Hang on. Let me make certain that I've. Okay. So, CLPFD. I'm going to start with the thing I always start with. What is my mother's height? Well, you don't know my mother's height, but you know some things about it. What can people tell me about my mother's height? Takes on my mother's height? Okay. All right. I'm not certain what's happened, but I'm not seeing responses to my question. So. But Chandra's typing. Okay, I'm not seeing response. Text messages are arriving slowly. Okay, all right. So, well, my mother's height, we may not know it, but we know that my mother's height is somewhere between some value we can set for, gosh, for the shortest human and for the tallest human. And so that establishes some range. My mother's not 9 feet tall, and probably my mother's probably taller than 3 feet. So that's a general range. That's what we call a domain. And my mother's height is also not a dict containing my name and address. It is not negative. And in the U.S., we measure things in height, feet, and inches, which will probably just represent in inches. And usually we round that to the nearest half inch. I'm 5'8.5". So there's a domain, a set of values something can take on. And this can be a powerful way to think about things, because with unification, you can have a variable that is unbound and you know nothing about it, or you can have a variable that is bound and that we know its exact value. But there are other things we can say. We can say, for example, with CLPFD, that X is in 1 through 5. Now let's make it a little more interesting and say that Y in 3 through 9, and that X is greater than or equal to Y. And it's smart enough to figure out that X now has to be at least 3, because that's the smallest that Y can be, and that Y can be no more than 5, because that's all the higher X can be. So we've constrained both of these variables to smaller domains. Well, this is great, but we're still just kind of printing out these odd constraints. What we really want is just some candidate numbers. So let's call label, and we pass it the things we wish to label, and it forces them. Yeah, we have to unify variables from Shakti's and Dad's height into the range expression. Yes. Yes, you're going to have to unify variables from Shakti's and Dad's height into the range to start the process off. Okay, so, and now it's going to give us the combinations. We have, we now have grounded ordinary Prolog values. Is this useful? Yes, very much so. I want to work through a very classic CLPFD problem, the send more money puzzle. This is an old riddle of assign the digits 0 through 9 to send to the letters SENDMORY in such a way that each one represents a different digit, and this is both, and if you write the digits out, then it makes a true arithmetic statement. So we can formulate this pretty simply. I'm going to make a list here out of SENDMORY. I'm going to constrain that list to the digits. This is ins. Ins is a convenience that takes the members of a list and constrains each one to the range on the right. We'll force them all to be different. And now I'm going to say what the puzzle is, which is 1,000 times S plus 100 times E plus SEND plus D. That's the send. And then the same for more. And that is equal to the same kind of thing for money. We then have an additional condition that we really don't want to start with zeros on the left, because that's the convention that we don't write zeros to the left. And then we want to actually label, we actually want to get an answer and not just a bunch of constraints. So and it gives us an answer, thinks it has choice points, but it can find no more. So, why is this interesting? Well, besides being useful from kind of a software engineering standpoint, it's useful from an efficiency standpoint. If I constrain X to, let's put X in a range. And I constrain X to be greater than 10. Now, if I constrain X to also be greater than 25, it still just reduces the domain. We have one constraint to check against, not 3. So what we're doing here is we're clipping off chunks of height. And we're only going to end up with one constraint out of the system. How does this relate to CHR? Well, I can write a CHR constraint in something of the form greater than XA and greater than XB, and A is more than B, then we can just get rid of B. So So CHR was originally developed, in fact, to write constraint systems. If you place ground in the if you check for ground in the in a guard in CHR, it will excuse me, it will defer execution of the constraint until it's ground, even outside of CHR. So if later on in the program you ground it, then it's going to go ahead and fire that rule. And that allows us to build constraint systems in CHR. Okay. So, I heard somebody say bafflement, Josh. It was helpful, but still baffling. Let's try and do a little bit of disembafflement. Can you say more about why you're baffled? I know that's a hard request. Okay, that's fair. Okay, so I have a problem I'd like you guys to work. Here's the problem. I have a chemical plant, and I have some kind of a big reaction vessel, and it has two modes. And I just want to constrain the value so that we only succeed when we're operating in kind of a normal fashion. And startup is the period when the pressure is less than 100. During startup, the temperature must be maintained between 150 and 250. And during run, the temp must be maintained between 200 and 400. So let's build a predicate that constrains the temperature, and of course it's going to have to be handed the pressure as well, because it's going to have to be controlled by the pressure. So you tell me what to write. Yeah, there has to be two distinct states. Start up and run. Okay. Oh. Tell you what, I'm going to write the head at least. Okay, so how are we going to make that vary depending on what state it's in? My apologies for yawning. I give these lectures at 2 in the morning my time. That's CHR, Patrick. That's CHR. We're in CLPFD. We could use a guard clause, but that would only test at the moment, and we're not writing code for the moment. We're writing code for all time. Which is just a little mind-boggling, but so we want to encode. We basically need an if here, but how are we going to encode the if? So, okay, can somebody suggest? Chandra making an explicit user input. Just kind of is, you're still thinking in terms of just this moment, but I want to do this for all time. I want to make it so the temperature is bounded to the ranges when we may not know what the pressure is yet. If nobody gets it, I'm just going to go ahead and talk about it. You guys are on the right track here. Okay, Patrick, yeah, that will only constrain it to being the beginning version. But Patrick's method's certainly close. We could do this. And Patrick, it's equal to less than. They deliberately don't define the less than or equal and greater than or equal operators for the other way because they want to leave the arrow free for users. Pressure less than, we can just use the less than 100. Okay. All right, lots of delay. Okay, so, all right, so this is one way of doing it is to say, that these have to hold, and then we could again use a Boolean. Temperature in, what were the other numbers I made up? 200 to 400 and pressure greater than or equal to 100. Okay, that does it. That will work. Normal operation. P and T, and then later on I can set P equal 45 and whoop. It will force it one way, and if I set the pressure the other way, it will change to the other side. Okay, but this is not a very intuitive way to do it, and there's a better way to do it. What we really mean is that when the pressure is under 100, that implies that the temperature is in 150 to 250. And when the pressure is greater than or equal to 100, that implies okay. So this is actually much cleaner. All right. So you can craft your sets of constraints this way. All right. How many of you have done some of the CLPFD tutorial? I know Josh said he had. I think at this point I'm going to ask if there were any of the methods or any of the predicates that you found confusing. Somebody in the European lecture asked about Otamatone 8. You're going to get choice points when the temperature equals 200. Yeah, you will. When the temp is 200. Well, your pressure, whoop. Let's try this again. The pressure can be anything if the temperature is 200. Let's make it 201, however. And now the pressure has to be in 100 to infinity. And can I go back to temperature from temperature to pressure? Yeah, sure. I just did it. And so I'm going to assume I've answered that. Of course, this is a constraint. So I, in fact, can do this later. And gets, if the temperature is 45, then that's going to constrain. Oh, is that true? Yes, that's true. The temperature would have to be in the 150 range. Um, okay. Let's make it 175. And now P has to be negative infinity to 99. Is it both ways? The operator, no. No, it's single implication. Because we're saying when this is true, then this must be true. We're not saying when this is true, this must be true. I have siblings, or I have brothers implies that I have siblings. I have siblings does not imply I have brothers. I might have sisters, but not brothers. There is a both ways operator. And for example, if we wanted to constrain it so that the pressure, that either the pressure was in a range and the temperature was in a range, or the pressure was in a different range, we could, or the pressure wasn't in that range and the temperature wasn't in that range, then we could use double implication. But the single implication form is far more frequently used. Okay, anybody have any questions about any of the predicates that appear? I thought anybody find any of them particularly confusing? If you've worked through the tutorial, you'll know that they are that it's mostly a long list of explanations of the individual items in the library. And I will wait to see if anybody has questions. If not, I think we're on to wolf, sheep, and cabbage. Okay. All right, with a long lag tonight, I think I'll just go on to wolf, sheep, and cabbage and come back if I need to. So, this is the traditional wolf, goat, and cabbage. It's called a sheep here. I'm going to work this in CLPFD. The way I'm going to work it is I'm going to make a list of lists. Each inner list will be of length 4, and we'll have for the wolf, for the farmer, the wolf, the sheep, and the cabbage, which bank they're on. And what I will do is I will build up the list going down, and I will keep adding lists of 4 unbound variables that have constraints to the previous section. And that's how I'll build up my series of moves. Okay? So I'll do that, and eventually then it will decide it's got a solution and pass that back in M. And then it's going to flatten that out and label it. When you flatten it, that's just so I can get a single list with all the variables that I might want to participate in the constraint system, and then I'm going to ground them all. Okay, so I'm going to look at the base case in a minute. I'll look at the main case here. All right, so this is the previous move, and I'm going to make the new move, which is going to have, the new farmer position, the new wolf position, new sheep, and the new cabbage. And then, since everything's either on the right bank or the left bank, I'm going to constrain them all to be, sort of mapping and filtering. Well, in this case, what I'm doing is I'm keeping notes about each of the variables, that is, I'm attributing them, and saying, this thing must have this relationship to these other things, and doing that for each move, and going and proceeding on as I do it, and sort of hoping that I will reach some resolution. So, okay, we already know everything's in 0 or 1 because it's on the left bank. That's a 0. Or it's on the right bank, which is a 1. Now, the farmer always has to row the boat, so the new position of the farmer, if you haven't figured it out, all the ends are new. New position of farmer has to not be the same as the old position of the farmer. Farmer has to row the boat. Now, we have the constraint that we can only move one thing at a time, which means that one of three things has to be true. Either the new position of the wolf has to be the same as the old position of the wolf, and the new position of the sheep has to be the same position of the sheep, or the sheep has to stay on the same side, and the cabbage has to stay on the same side, or the wolf has to stay on the same side, and the cabbage has to stay on the same side, right? Each of those just omits one of the three items. So that allows us to move one item at a time. And then there are just some rules of the game, which basically says that if the sheep and the cabbage are on the same side, then that implies that the farmer has to be on the same side, right? And this is just a common sense thing of if the cabbage and the sheep are on the same side, the farmer has to be there to prevent the sheep from eating the cabbage. And then the same with the wolf and the sheep. If they're on the same side, then the farmer has to be with them. Fine. So we've now constrained this NM. We've constrained all of its elements. And now we can reconstitute our list of moves, putting NM on the front. And I had to stick this back on because I'd taken it off. That's the prior move. So this move, prior move, and everything else. And we go on down. But how do we do a base case? Well, bizarrely, the base case is when we can unify the last move with 1, 1, 1, 1. And so, strangely, This does a whole lot of computation because we have all these constraints and they depend on the constraints in the previous one and so on. So when we hit this expression, it goes, let's see, is that possible? When we start, we're at 0, 0, 0, 0, and everything's ground. So that can't be 1, 1, 1, 1. And then after the first move, we have some constraints, and we see if we can get there in one move. And we can't. So this is going to fail. So, but each time the set of possibilities gets larger. This is the common experience we all have, that it is easier to predict the future tomorrow than it is to predict the future for months in advance. I will, tomorrow I will I predict that I'm going to go get my lease signed because, and that's pretty, likely and pretty specific, and maybe it won't happen, but it probably will. But what's going to happen to me, on some morning 3 years from now, who knows? There are many possibilities. So our knowledge of the future is always dimmer, and at some point we're going to see that we can imagine being at 1, 1, 1, 1. So it's going to give us a set of moves. And interestingly, it always gives the shortest ones. It gives the shortest ones because it's going to, because this is first. So is this stuff kind of magic? Yeah, it kind of is. You just say what your constraints on your variables are, and it sort of runs it. I will tell you that the downside of it is that if it runs it slowly, you are stuck fiddling around with the options to labeling 2 in order to make it operate. Okay, do we have questions? Comments? It gives the shortest because this clause is first. The first thing it will try is simply to move everybody to the left bank. It is simply to say, okay, now everybody's on the left bank. And, of course, the constraints are get looser and looser and looser for each, because there is some wiggle room. There's more than one way of mapping each move to the previous one. So yeah, there's only, a few dozen possible. There's only like about a dozen possible first moves in a chess game, but the number of possible chess games grows enormously. So because I put this clause first, it's going to first try to unify and stop it. Okay? All right. And Okay. So this kind of constraint, if you've ever worked with anything like a CAD program, constraints are actually used widely to program this kind of thing. In fact, I have YED up. This is YED. YED is a graph editor, and I will make this larger. Hang on, I'm going to get rid of these. And okay, now I want my graphs to look nice. So if I pull this up close, it does this little snapping action. That's actually a constraint system at work. And hey, there's a constraint, and there's a constraint, and we've all seen these kinds of systems at work. And, you know, I can get one down here, and have constraints. And I can make a nicely structured diagram because it looks for these constraints, and when they succeed, it draws the little icon, and then it probably has a somewhat looser constraint that's like is within one of, and if it gets within one of, then it does the snap action. So that's a practical use of constraint programming. I actually made an attempt at making a startup that depended heavily on this. We were building online CAD systems. But yeah, many computer-aided drafting systems depend on this behavior of constraints. Design rule checkers. If you ever made printed circuit boards, design rule checkers are all about constraints. Okay. All right, I'm going to wait one more time for questions. I see Josh typing. Yeah, it's CLPFD is a very cool system. I use it quite frequently for various things. Okay, and all right. Yeah, Automaton 2 or 3. Let me tell you, Automaton 8, I've never quite figured out. It's there was something I didn't understand about it, and I could never get Marcus to answer the question, so I just kind of threw up my hands and said I'm not going to stop for that. Yeah, the online CAD idea was you know, I'm going to talk about the online CAD system, eModelWorks. Yeah, it's a true expression of Prolog's intent. You get non-binary answers to questions. It is, Patrick. Yes, CLPFD. Marcus would argue that. He would be applauding your statement. Okay, Automaton. Hang on. Let me find Automaton here. All right. An automaton is a hierarchical state machine that only contains paths that are within the language. So basically, if you can run through the machine and end up in what's called a goal state, the blue state in this case, then it's in your language. And this is sometimes called a recognizer. And this, for example, takes a 0 followed by any number of zeros, followed by a 1, followed by a 2. And yes. And so you can make recognizers this way. Automaton 8 adds the ability to add counters to it. Okay, going back to the online CAD system. Here was the basic idea. It would be lovely if you order something to have it made, it's a nightmare. It's a nightmare on both ends, because even if you have a CAD system and can, exactly specify what's to be made, then there's a manual process while that is translated into a set of so-called G-code instructions that actually drive the computerized machine tool. And that was a crazy thing to not be automated. So I began to think about it, and while being a machinist takes quite a bit of human skill, in some respects, being a CNC machinist takes a little less, because the machine does much of it. And I was thinking, well, I used to be like part owner in a little engineering works, and we had a slant bed lathe. This was an expensive machine that had a very dangerous machine. It was very easy to either damage the machine by misrunning it, or hurt yourself. And so, naturally, if you just showed up, we would not allow you to run that machine, just without assuring ourselves that you were competent. And yet, it's a cool machine. I'll make almost anything that's round. So if you need a new hub for your bicycle that the manufacturer's not around anymore, this would be just the thing for you. So you'd have to come to us with your old hub. We'd have to figure out what it looked like, make a drawing, and then convert that drawing to a set of instructions for the machine. And if we made mistakes doing it, we could harm the machine, so we had to be very careful, and the whole process is quite awkward. But if we encode what the machine's limits are as a constraint system, then we can allow you to send us the part drawing, we can allow you to just send us a set of instructions to feed to our machine. But like I say, and there's lots more people who can make those sets of instructions than there are people who have the machine. So if you send us a set of instructions, we can verify them, then we don't have all of that labor, and that dramatically reduces the cost of machining. So that's what we're working on. And if anybody has a few $100,000 that'd like to invest, I'd be happy to talk with you. So yeah, that's what I was working on. Um, and This is the last time we'll do something in synchrony. So I have a request from Ian to please fill out a feedback form, and I'd like to see what you have to say about the class. This is the second time we've run this class. We ran it for the first time in 2018, and we're now gearing up to give more classes. I will give you a little preview. We are going to be doing a chatbots class soon, class on writing conversational agents, and we really want to learn what we did right and what we did wrong, and so we can fix it. So please fill that out. It's been lovely having you as students. Class does not end until Saturday, but like I say, this will be the last time. This is the last lecture, and after the end of class, class materials will stay up and be available. The Slack will continue. I will perhaps be less of a constant presence on it. There is, if you're still studying, and feel free to reach out to me if you have questions. The OpenSim will remain up and accessible until basically until we next need the server, which I believe we will for the chatbots class. So that'll remain up for a few weeks, and then it'll be taken down. But it's been lovely having you all. This has been a great experience on my end. I hope it has been on your end. And thanks. Okay. Yeah.